Okay.
Go ahead.
So Dave asked me, and in talking with Peg too, and we thought would be a good presentation tonight. Basically what I'd like to chat about is just an overall kind of a 50,000 foot view of what are sealants. A lot of you hear the terms constantly about caulking, adhesives, and sealants. Well, what does all that mean? And unless you're really into this, on a regular basis, it may be a bit confusing. So I just kind of would like to give an overall view of the sealants and caulking and adhesives, what some of the differences are, dive into a little bit to help you understand what it is you may be specifying, what the different, products may be appropriate for different uses and whatnot. I mean, at the end of the day, we're trying to protect our buildings and structures. And we were talking earlier, water is the root of all evil. You have to keep everything out of that building. And knowing a little bit and understanding what the difference is and what to specify and what to direct on your buildings will help not only keep them looking beautiful for many, many years longer, but also will help protect them structurally, and it makes a big difference. So we'll spend a little time kind of going over that. There's a lot of different technologies out there, so we'll dive into that as well. And, we'll talk a little bit about pros and cons on each of those as we go forward. I guess probably the best way, if anyone has any questions, probably just jot them down. You may find as we work through the slides that those questions get answered, but I'd love to have a question and answer period at the end for anything that you may want to discuss. So I'll just go ahead and move on. So what is a sealant? There are different types of sealants, and how do they protect buildings? Well, let's go find out. And my slideshow is not working. Hold on a second here. There we go. I'm going to shrink this up a little bit. Sorry, bear with me. I'm kind of blocking my own screen view here. Hold on. I can collapse that a little bit. There we go. All right, so in today's world, there's a lot of different technologies. There are many options to help create airtight buildings. So caulk, sealants, and adhesives, they do play a major role in keeping our buildings dry, bug-free, draft-free, all the different things that you want when you're actually designing and specifying a building. Some of the products are multi-purpose, and others are more project-specific. Some of them need to be used in different areas, perhaps on different locations of the structure. So let's get into it and understand the differences. It can help you make an educated decision as to which product will better fit what you're working for. And why is this not working? One of the things I wanted to chat about real quick was a joint and expansion. This is a quick overview of what goes on with a joint a little bit, and just to kind of set the stage for some things that we'll get into a little bit. There's different effects of expansion and contraction on joint sealants. Some people may think that in the middle picture here, where everything is flat, that is what you want to for your designing the joint. And we'll get into some specifics a little bit later about how this actually works. But there are different things that are going on with joints. They don't just stretch apart, but they also compress together. A perfectly really designed joint will look like the picture on the right at application. You want a concave finish, and you also want two-point adhesion. If you can see my arrows as I'm pointing to that, what this round piece in the middle represents would be like backer rod. So you really want two-point adhesion to get the best results out of anything that you're specifying for joints. The part here in the middle, the circular part that represents backer rod, you'd like to use a closed cell. Some people do not specify that. There's open cell and closed cell. Closed cell works that in the fact that the product, the sealant, will not stick to a closed cell versus an open cell. An open cell, the sealant will sort of absorb into it, and it creates more of an issue. But if you use a closed cell, you get two-point adhesion, and two-point adhesion is what you're really ideally looking for. The main reason being that if this joint were to expand further, you get the ability for the product to stretch. However, joints also compress, during different times. They're not always moving away from each other. They move towards each other. The concave motion here helps allow the sealant to move up some and then while this is a bit of an exaggerated picture to the far left, it takes the stress off of the substrate adhesion points by having that flexibility. So the concave measure is what you want. Typically, when it will stretch together, it will then look like the middle picture and have more of a flat, smooth finish. So we'll dive into that a little bit later, but I kind of want to set the stage for what to expect perhaps for joints. There's different stresses on building joints. This picture, people don't always think about the different, there are really 3 different stress points for a joint movement. If you have your joint here, you can see my arrow, there are different flex points. They're of course moving into each other, or they're moving away from each other, which represents the arrow here to the left and the right. They also can move up and down a little bit. You may have a substrate that, say, is exposed to sun a little sooner than another part of the building. It may expand, which will then put an upward pressure, while another one may be pushing down a little bit. So there's a movement of up and down. There's also a movement of front to back. So while one part of the substrate, again, may heat up sooner than the other or cool down quicker, it can create a flex in 3 different motions when you're looking at a sealant. So it's a very critical part of your building design that you have something that's capable of handling all of those different movement capabilities. So just some quick common reasons why sealants do tend to fail. Obviously, number 1, inadequate surface preparation and/or application. Okay. So one of the common denominators between any of the sealants that we'll cover is you need a good clean substrate. You know, if there's mold, mildew, dirt, you know, anything loose or chalky or kind of, you know, maybe gritty there, it needs to be cleaned, it needs to be prepped properly, and then the application that follows needs to be done properly and according to the manufacturer's specifications. Another reason products fail is low performance sealants and high movement joints. You'd be surprised, like some of the joints that we just looked at in the previous slide, where people are using some very inferior sealants and they just simply cannot handle the movement that's taking place in that particular joint. Another issue can be incorrect sealant products in underwater or below grade applications. There are sealants that perform great in submerged surfaces, and there are others that perform great above, but you would never want to use them on the inside of, say, a fountain or something like that. So there's a difference in where the product is going to be used. Some of the ones that perform great below grade are not so good above grade and do not handle, say, UV from the sun very well. Another issue that can cause problems is just simply incompatible, sealant and substrate incompatibility. It does cause an adverse reaction at the sealant substrate surface in the interface in the substrate there, where the 2 products just don't really seem to like each other, where you're putting the particular sealant on and it may not adhere very well. You have to have adhesion to keep a joint and working properly and lasting long. There are other products that can cause issues. Acetoxy silicones on porous or natural stone substrates. Those can cause some staining and hydrophobic bloom. We'll get into that a little bit later. You may have seen this somewhere in your travels, but some silicones can actually stain the substrates they're on, which can be a problem, and they may not be the best choice for that particular area. Urethane or incorrect sealants as a glazing cap bead, they can yellow, and the UV breaks them down pretty darn aggressively. As a result of UV breakdown, a lot of times you will see also the next item, which is reversion or degradation of sealant. UV, given enough time over certain chemistries, will literally break them down and cause them to ultimately liquefy again. They want to go back to where they started, so they will revert back down to a liquid form. The other problem that can cause it is stress and relaxation, and what that means is there's a stress if joints are, say, expanding, so you have to have enough elongation to handle that. But there's a relaxation time. As the substrates cool back down, they may move back together, and some products cannot go back to their original size before they started the stretching motion. If they cannot get back down to their original size without some failure, that can also cause problems and water intrusion as you move down the lifetime of the building. So let's talk a little bit about what the heck are sealants, adhesives, and caulks. Okay, well, a lot of times these terms are used interchangeably to describe products by professionals, consumers, you name it. You'll hear those three terms a lot of times, and you have to sometimes dig to get to what is this person exactly asking me about. Let's make sure we have the right understanding and define the word. They all do work as a substance used to block the passage of fluids through the surface or joints of openings and materials. They also serve a common purpose of blocking dust, sound, and heat transmission. You hear sometimes where people are specifying a sealant that meets some sort of acoustical specification. You know, really that's just basically a test that somebody may or may not want to pay for as a manufacturer. It's a pretty expensive test, to be honest with you. But if you think about it logically, any caulking or sealant that is closing up a gap is going to reduce sound transmission. So, you know, that's one of those things that some folks look for, but I will tell you pretty much any caulking, sealant, adhesive will meet that standard. So sealants, adhesives, and caulks, performance versus aesthetics. A main difference between sealants, adhesives, and caulks is the elasticity and strength, and that's really the biggest thing that you're going to be looking at. A simple way to think of these types of products is that sealants form a flexible barrier. Adhesives bond materials together. And then caulks can be used for aesthetics, such as painting and medium-duty applications where the use of an actual sealant is not required because the anticipated joint movement is not that strong. For the aesthetic brand of caulking, typically an ASTM C834, and we'll get into this a little bit too, will meet that grade. That is typically what you're going to see used on the interior applications of structures. It's what you typically would have used to, say, caulk your baseboard up to your wall before painting, your door jamb up to your wall. An 834 gives you an aesthetic look, but it also is a sealing capable product as well. So that's one of the two differences you're going to find when you get to the acrylics or acrylic urethanes are the two grades, and we'll get into this too a little bit, but C834 and ASTM C920. ASTM 920, again, acrylic technologies that meet higher performance standards. They can typically perform well in place of an ASTM C834 caulk, but they are also expected to show way better movement capabilities, way better increased elongation performance, better adhesion, and better durability as well. So they can give you the aesthetics that you're looking for, but they also give you a lot better performance. Typically, these are the products that you will see used on the exteriors of structures or homes. Certain states actually mandate that even home building, new home construction requires at least an ASTM C920 product on the exteriors. So what is caulk used for? Caulk is used basically as a sealant, filling cracks, gaps around windows, doors, plumbing pipes to prevent water, insects, or air from entering your building. Caulks are flexible when dry, but they're not elastomeric and are intended for use in areas with minimal expansion and contraction. That's where the C834 is referred to often as a caulk. There are a lot of caulkings out there that claim to be painter's caulking or joint fillers or whatnot, and many of them don't even submit for the C834. If I were specifying a structure in any way, I would definitely make sure I had at least a ASTM C834 throughout my interiors. You'll get better performance. You will get a better look. They're typically better made, less prone to cracking, and from an aesthetic and performance view, they're really a much nicer product. So, you know, try to stay away from any of those sealants that don't even cash in at the 834 level, because you really don't know what you're getting with those kind. So let's talk about adhesives a little bit. I think a good way to look at adhesives is probably, again, a little shout out to Peg because she's an PPG person. So liquid nails might be a great kind of thing that we all know about as an adhesive. An adhesive is used for, it can also be known as a glue or cement or paste. It's applied to one surface or both surfaces of two separate items and binds them together and resists their separation. Adjectives may be used in conjunction with adhesive to describe properties based on the substance's physical or chemical form, the type of materials joined or condition under which it is applied. Typically, you'll see adhesives used in, say, carpet adhesive, ceramic tile, concrete, countertop lamination, flooring underlayment, drywall lamination, some different other areas that we mentioned here. Adhesives, you know, people can use caulking and sealant as adhesives, and some do, but they're not specifically made for that at all. So the adhesive application, again, typically a little more glue. They tend to be a little more chemically cured or moisture cured. They'll probably dry quicker than what an acrylic would for an adhesive type use. So they do, excuse me, they do have their place, and then you'll see them used for that. So when people refer to caulks and sealants as adhesives, to me, you know, that's a little bit of a different use. Again, we do have some customers that use it for that, but generally getting a traditional adhesive is probably a better way to go. So sealants, what are they used for? A sealant is a material that can be applied to a gap, joint, crack, or opening in a paste or liquid form that cures or hardens, forming a seal, a barrier against gas and liquid entry. They are made from flexible material, making them ideal for areas prone to expansion and contraction. ASTM C920 compliant products are typically called sealants. So you have a lot of solvent-based products that meet the ASTM C920. And if you're working in the acrylic products, definitely make sure you find one that's rated with the ASTM C920 as well. That will give you the expansion and joint movement that you're looking for in the exterior of structures. A typical minimum flexibility for an ASTM C920 is going to be at least 300% elongation. Your best ASTM 834s are going, or 834s, I'm sorry, are going to give you maybe 250% elongation, and those are the best. Typically, they're going to run around 175 to 200. So, and if I were specifying an exterior of a structure at all, including a home, anything, I would make sure that I would be okay with acrylics to make sure that everything that I would specify, though, is a C920. Again, a lot of those, again, will be a minimum of 300%, and you can get up to 800% elongation with that formulation in those products. So sealants, basically, in short, higher performing, bigger joint movement, and what you're going to want for your exteriors typically. Here's an overview, though, now that we've talked about some of the terminology of the different chemistries that are out there. This is an overview, and we'll dive into a little bit on all of these. But you basically have 5 different categories today that you can choose from that will meet your different needs in establishing, you know, waterproofing your buildings or specifying what you would like for your sealants. There are latex acrylic products. There are polyurethanes. There are silicones. There are hybrids, and there are solvent-borne hybrids, and there are acrylic urethane hybrids. So these are generally your 5 different chemistries and what you're going to look for as you move through it. The latex acrylic to your far left, I would consider this your acrylic 834s. There's 2 different chemistries on how things cure in sealants. With your waterbornes, whether they're acrylic urethane or latex acrylic, they're an evaporative cure. So what that means in an evaporative cure is that the product dries as you would expect, like, you know, anything that you would do, like wet paint in it, for an example. You put a coat of paint on, the product dries, and then you're left with the product. It is an air-based, air-drying chemistry. Polyurethanes, silicones, and the solvent-borne hybrids all use a chemical cure. They're basically moisture cured. So what they do is they take the moisture that may be in the air and they cure with that moisture. So it gives you some different performance attributes, and there are some pluses and minuses to each of those. The one thing about the polyurethane, silicones, and the solvent-borne hybrids is that they typically will reach a full cure a little quicker. As a chemical cure, they will cure faster. So if you were to do performance adhesion tests or things like that, they'll be a little bit quicker. The latex acrylics and the acrylic urethanes will take a little longer to cure, but what's interesting about them is that they're typically, if the substrate is going to be painted, they could be painted over quickly. They do not need to have a full cure before painting. So you can apply those products and paint quicker and get on it faster in that regard. But because the sealant system is compatible with the paint coating systems that are being used today. If you're using the other products, the solvent-borne, you need to give them more time before you put any kind of paint on top of those, because they need to cure, and then they have a, basically it's referred to as outgassing. So as they're curing and outgassing, if you put a paint film on those too fast, it could potentially affect the performance of the paint and coatings. It could also stain the paints and coatings where they will have some issues and not look quite right aesthetically. And it can cause some problems in that regard. So we'll dive into these a little bit deeper, but that's a quick overview of really the 5 different technologies that are out there. So let's talk about the waterbornes and the basic caulkings. The strengths cured by evaporation of the water. This is the products that will typically be 834. They're residential, commercial construction, weather sealing, painting, and more. They're easy to use and clean. You can clean up with water. You do not need solvents for cleaning. A lot of the other technologies that are out there, you have to use xylene or mineral spirits or alcohol to clean those. The other good advantage of this product, those basic waterborne product, odorless, very low odor, so it's not offensive to others. And it typically gives pretty darn good adhesion to most construction substrates. Limitations though, not for water immersion. If they are constantly submerged, the waterborne basic caulkings and whatnot are not going to perform under constant submersion. The water eventually will break them down in time. Now, when I say that, if they're wet a few days and they have a time to dry out, if you have an incredible rain season or whatnot, that's okay. It's basically where you cannot have them being underwater for 30 days straight. They're also limited in that they're not necessarily a construction sealant, so you're not really going to use these for high-rise structural applications on the exteriors, and they're not typically used for high heat applications. So there's some of your limitations on that. Silicones. So been around forever, great product. There's some different silicones that are out there as well. You have 3 types of cure: neutral, acid, and chemical cure. Neutral and acetoxic cure by a chemical reaction with moisture, just kind of like all the others do. They react with moisture to get their full cure. A chemical cure sometimes does require an activator or a catalyst. You'll see there are some 2-part products that will need to be activated in the field during application. Silicone, actually regular, normal kind of silicone that you're used to seeing is getting sort of hard to get. There's a bit of a shortage out there right now, and it's being, they're moving to higher end silicones that are used in this electronics, avionics industry, structural glazing, different things like that. And silicones are definitely getting a little tougher to get. And when you do get them, they're getting to be very expensive right now. But they definitely are being moved into the higher end areas. Great strength of silicone. They're very water resistant, very durable, and it stays flexible. Heat resistance for silicones, fantastic. If you have a area where you think this is going to be a very high heat area, they're fantastic for that too. And their adhesion to glass is phenomenal. And as a matter of fact, I will mention this now since we're talking about it, because a lot of times people wonder, okay, what's the difference between acrylic caulking and siliconized acrylic? The siliconized acrylic has a very tiny amount of a relative of pure silicone added to the siliconized acrylic caulking to give it the ability to stick to glass better. So when you hear siliconized acrylics, that's really what that's all about. There's an additive there that's from the silicone family. It's not pure silicone, because you wouldn't be able to clean up with water if it was pure silicone. But it's a relative in the silicone family that's an additive that gives acrylics excellent adhesion to glass with that particular additive. So just a quick little point there while I was thinking about it. Some of the limitations on silicone: does not hold paint. Silicone will not even stick to itself, so you could not recaulk over silicone. You cannot paint over silicone. It's just not going to happen. It also has poor tear resistance, which is kind of an interesting phenomena to silicone. It's extremely durable, and I have seen silicone last for ages. But a really interesting phenomena about it is, let's say, going down a window frame at a storefront. Should there be a rip or a tear in that particular silicone where the cut may be, maybe a pressure washer gets on it too hard and cuts into it, it is super duper easy once that tear happens to grab that and pull, and the whole thing just gives way. I don't know if anyone's ever been in an old house where they've had silicone around a tub maybe, or some plumbing areas, and you've seen that silicone. Once it comes up, you can just pull it out, and it just, like, the whole string of silicone will come loose. So it's a very interesting phenomenon. I'd have to get with my chemist to explain why that happens, but it is an interesting thing that happens with that. It also has poor alkali resistance. So with acetoxy silicones and cement or masonry, it will definitely can cause an issue and require a primer over the areas next to it that you plan on painting. It can attack substrates and cause corrosion on metals, and it can stain or bleed into the substrate, which is referred to as hydrophobic bloom. So if you've ever seen, again, talking about storefronts, since we just were, you may go around an older storefront and see that they have perhaps bronze windows around it, and you can see where the silicone sealant, if you're a nerd like me and look for things like this, but I challenge you to go out and do it now that we're talking about it. If you go out there, and you'll see where the silicone is touching maybe the aluminum window frame, there's a discoloration that takes effect from the silicone into the metal frame. It actually seeps into the aluminum metal and discolors it, oftentimes causing it to lose its bronze or black window and whiten out. So there is a hydrophobic bloom there that is just a natural result of the silicone technology. You have to have solvents to clean up during application, and the odors are very strong with silicone typically, especially acetoxys. I mean, acetoxys are pretty solid, but they have a very vinegary smell, and it's sometimes can be a problem depending on where it's used. So let's get into polyurethanes a little bit. Again, this is a chemical cured product that uses moisture in the air to cure. The strengths of it, it cures pretty fast, actually, which is one of the great things with the moisture cure. You need to give it some time before trying to paint over it or anything like that, but it does cure, and it will probably be the best it will ever be, probably within, say, 5 or 6 days of its application. That's going to be the best a polyurethane is ever going to be for that particular structure. It's used in automotive, industrial. You'll see it a lot in parking areas, sidewalks, gutters, construction adhesives, and tilt up. It has really good tear resistance compared to, say, silicone. Has great initial adhesion, and the big strength it has too is that it is good for continuous water immersion. So if you're using below grade, I would definitely recommend staying with polyurethanes inside a fountain or something like that. Look at polyurethanes. Limitations on it, though, it does have a very short shelf life. The product needs to be used within a certain time frame, or it will not. It's just going to go bad. It just won't be there to use. If it's a two-part poly where you have to mix it, you have typically a very short life on putting the application in place as well. The biggest urethane limitation, and kind of in my mind, is when you have unpainted joints and the UV. Polyurethane struggles with UV. It will break it down. I'll show some pictures a little bit later in here, but I would just challenge you to go by a shopping center or a tilt-up facility or anything like that, and you might see surface grazing cracking on the joints in between the concrete panels. That is the UV absolutely breaking polyurethane down. It does not hold up well to that. It's also not very easy to paint. Some require a solvent white before painting. Some require a special primer. And they're not really compatible with the acrylic coating systems that are used on the exteriors of buildings now. They're also very difficult to tool. They are hard to work with, hard to gun, especially in colder temperatures. They're very difficult. They do have solvents in there to clean up with as well. We'll talk about plasticizers here, which is something that's used to help make product flexible. We'll especially get into it a little bit with the hybrids. And this is a product that wants to revert. Given enough time and a UV exposure, polyurethane would eventually liquefy again, and because of the UV. It just does not handle UV very well. Has its place, but it has its struggles, just like everything. I wish there was one magic bullet for everything, right? But we all know the world doesn't seem to work that way. So let's get into the hybrids and polymers. Again, strengths, it cures pretty darn quick with a chemical reaction with the moisture. It has a really fast strength buildup, good initial tact. The adhesion is pretty strong with the hybrids and the MS polymers on the front end. Great water resistance. And what's great about it too is, like the polys, it can be used below grade. If you don't have UV interacting with it too, it really holds up, performs great. You could use this inside of a fountain or an area that's continuously wet or moist. You're not going to have any problems with it at all. It's used for construction, windows, doors, kitchen, bath, roofing. Some of the hybrids and polymers, you'll see some of the roofing guys use those for some of their flashing systems and things like that. You can use it inside or out. It is water resistant, durable, and flexible. Good adhesion to glass. It is paintable, but it can cause shiners, and we'll get into that a little bit too. One nice thing about this compared to most of the polys, it doesn't have the isocyanates, which are some things you kind of want to try to stay away from if possible. And some formulations are even phthalate free. And relatively low odor with this product, which is pretty nice. Limitations, as with the polys, you have a short shelf life, and the UV resistance is really just not there for long term. Again, hard to work with, very difficult to paint. These also, some are paintable, some do require, though, a special primer or a solvent wipe before painting. You got to clean up all the tools and application process with solvents. It also is subject to reversion back to a liquid form given enough UV exposure. Not quite as bad as the polys, but they can happen. The biggest thing with the hybrids and MS polymers, though, are the plasticizers. And I think this is probably a good time just to give you guys a little intro to plasticizers. They're used as an additive in certain formulations to help give caulking and sealants additional flexibility. Some plasticizers used within proper ratios can be a benefit. They actually kind of help soften the contact point where paint and sealant touch, and they can work pretty well. The problem is to get to some of these movements, and a lot of times when we talk about the ASTM C920 sealants, I'm sure some of you have seen class 25 or class 35. A lot of these will be made to class 35 or class 25. The cheapest, easiest way to meet those test certificates and have that flexibility is to add plasticizers. But to reach a class 35 or sometimes class 25s, plasticizers are so overloaded in there that all they've done is meet that test. It's like a product has been made to be a class 35. And if you think about that movement-wise, we're already talking about a class 25 on most ASTM 920s, which means that's a pretty massive, that's 50% joint movement to be a class 25. If your building is going to where you need a 70% movement, I think we're in the middle of an earthquake and not quite so worried about, the performance of a 25 versus a 35. How much is enough, right? So if you're testing to meet a certain number, it can be done. But you lose attributes that make the sealant overall a whole lot better. So a class 25 in 99.9% of the world's cases is plenty for anything that's going to be going on in the real world. You can create a product to meet a particular spec, but you're giving up a lot of different other things to get that. One of the main problems with plasticizers too is their effect on the paint coating system. Should the product be painted, I mean the sealant or joint be painted, plasticizers will leach out. When they leach out, they attack the paint that's been put on them, and they tend to affect the performance of that paint. What'll happen is, and some of you may have seen this somewhere, over time, is that you can go to a structure or a building and you can see everywhere that a line of caulking or a bead of caulking has been placed, there's mold and mildew growing on that particular area, right where the caulk beads are. The rest of the paint job can look fine, but where those caulk beads are or the sealant beads are, you see mold, mildew, and dirt. What's happening there? The plasticizers leach out of that. They soften the paint film. The paint film becomes tacky and sticky. Dirt, mold, mildew land on that. They grow, they thrive, and it can absolutely affect the performance of the paint coating and the aesthetics of the building in a big time way. I actually looked at an apartment project one time in Florida where a competitor of ours, and I was just asked to come in and just give an evaluation of it. And there were 13 buildings in a giant apartment complex where mold and mildew were everywhere the sealant was put down. And the project was only 6 months old. So it was, you go over, you feel it, it's tacky, you can see what's going on there. The only way to correct that issue is you have to clean it and put a special primer on and then go back and repaint. So, good luck having all that paint touch up and match. So it's a performance issue and an aesthetic issue when products are overloaded with plasticizers. So if I were writing specifications, that's one of the things I would take into consideration because I have seen it multiple times where it's been an issue. So acrylic urethanes, this again is like the higher end version of the acrylic caulking that we talked about. This is assuming we're at ASTM 920. They also cure by evaporation of water. So a little slower cure on the front end, but more paintable, faster. They do have an excellent adhesion to common construction substrates. It's used in residential, commercial, weather sealing, waterproofing, tilt-ups, you name it. You can use these inside, probably a little overkill for interior uses, but it can be used. Super paintability. The acrylic urethanes are compatible with the acrylic coating systems. I mean, if you think about it, everybody remembers oil-based alkyd paints and different things like that. Those work great over solvent-borne sealants, right? But we're using acrylic coatings today. Acrylic coatings are what's out in the real world, what are being used, and what perform best. So having acrylic coating systems, sealant systems that are compatible with those are definitely a win, and helps eliminate some problems. Also easy to apply and tool. Clean up with simply water and low VOC and the low odor and odorless during the cure time. Big limitation. Acrylic urethanes cannot be used for water immersion and not for below grade applications. They are also not recommended for structural skyscraper type applications as some silicones are. So they're not a structural sealant for glass windows on a high-rise buildings, things like that. So talking about the acrylic performances, I may have covered some of this, but there's acrylics that are basic caulkings, 834, and then there's elastomeric 920s and acrylic urethane 920s. The acrylic urethane technologies are different than poly, silicone, and hybrids. They're waterborne. They cure through evaporation. Silicone, polys, and hybrids cure by reacting with the atmospheric moisture. So the acrylic cures by water evaporation, which allows individual polymer particles to come together and melt into a continuous film. Reactive chemistries of the others cure by reaction with moisture, which catalyzes the product to perform. So that's some of your chemistry differences on the technologies. You definitely want to look, again, it's super important if you're specifying acrylic products, that you look for a product that's been engineered for exterior control joints and commercial waterproofing for your exteriors, and you're pretty safe to go with the 834s on the inside of your structures. Talking about acrylics, just to kind of give you an idea of what's going on in that chemistry as well. This chart, I won't spend a ton of time on it, but when you're looking at acrylics, I would guess compare it to buying a car, right? You can get a base model with a stick shift. You can get a better model with better sound system and an automatic, and you might get the best with all of those things that has a sunroof and leather seats, right? So what makes up the difference a lot of times are pigments and fillers. Those, like if you can see my arrow here, that's kind of what's represented here in this green. There's typically what you'll find in acrylic chemistries. There's a bit of water added. There's pigment and fillers. There's the acrylic latex resins. You can have some plasticizers. Typically, a little mineral spirits are in there that are required to help the chemistry move from the tube to the substrate that you're putting it on, and there'll be different performance additives. As you get into the higher ASTM 920s, you'll notice that the pigment and filler section is a whole lot less than what the resin is. Resins are more of the performance product that's in there. Now, the better acrylics are going to have a higher resin content and not rely on plasticizers. There are resins that give you excellent flexibility. They're a little more expensive, but they perform better, and you don't get that plasticizer bleed through. If you're looking for a performance product relying on plasticizers, you can have the issues down the road. But the resins, a higher resin content of an acrylic is what separates the interior products versus the exterior products where you get the performance. So that's just a quick techie sheet there if you want to take a look at that sometime. So let's talk a little bit about, we talked about the different chemistries and different decisions that can be made in your specifying. Let's talk about preventing water intrusion in buildings. We kind of chatted on this as we were all warming up here a little bit about water leakage. It is a major issue with problems. I mean, you can cause physical damage to the building. You can have adverse health effects, compromised indoor air quality with interior mold and mildew issues, health concerns from mold growth, especially in medical facilities and nursing homes and things like that. There's fire hazard that can result from water damage, slip and fall hazards. Your energy bills are going to be higher, and the absolute structural integrity of your building will be there, not counting the stains and just, aesthetic point of view. And we talked a little bit about this earlier. I kind of stole thunder from this, but this is a sheet here that this page will kind of show you a little bit of what we were talking about with the joints. To the left, this is a 2-inch properly designed joint. I think this will give you an image of what the drawing to the right shows. This is a couple pieces of masonry that we have here. This is the closed cell backer rod in the middle that we discussed that allows you to get the 2-point adhesion. So the substrates, you have 2 points of the adhesion here. If the sealant were to go all the way down to maybe where the joint ended, that gives you 3-point adhesion. That puts additional stress that actually helps contributes to a proper joint failing sooner. So not only does your applicator save a boatload of money by filling gaps like this with backer rod that comes in various sizes, it actually gives you a better joint by having strictly 2-point adhesion and not 3. So this is what you would want when you're specifying a building and what we typically see in drawings and plans. The drawing here to the right is just an example of it. Again, a properly designed joint. The joint should not typically exceed more than 2 inches. We get more than 2 inches, we've got some kind of issues. Even in tilt-ups, you don't see that all that often. And the ratio too, just in case everybody's wondering, a joint fill should be no deeper than half of how far it is across. So for easy math, if we were doing a 2-inch joint like we're doing here, the sealant should not be any further down than 1 inch deep. And that's probably even overkill. But on the sides here, that's about where you're probably going to want to be. But that's a great ratio to remember if you're specifying some projects and someone asks you, okay, hey, this joint is 1 inch deep by, 1 inch wide. So, what you would recommend at that point is, okay, you want to fill that with 1 inch wide, but go a 1/2 inch deep, not a full inch deep on your spec. So choose the right sealants for moisture control. You want something highly elastic that bonds at the molecular level. You want something, honestly, that can get to the 2-inch gap because you never know what may happen out there. You want something with a great mold and mildew additive package, something that's good in all weather conditions, can be applied in most. You also want something that will be long-term, maintain its high elasticity and adhesion, even after years of exposure. I'd also look for superior adhesion to construction materials over long periods of time. Some of the ASTM tests that are out there really only test against 3 different substrates. So that typically is glass, metal, and masonry. There's a million other things you guys are speccing on your buildings out there, you know, from hardy board siding to a million different things. So wood and whatnot, there's just a ton of different things out there, different vinyls, different things like that. So do a little research, make sure you're comfortable that the adhesion to multiple construction materials is there for you. You also want something that's not going to lose its bond or elasticity under varying mechanical stress. Non-aging, non-sagging. When we talk about sagging, a lot of times people refer to that as hang time. How thick can you put the sealant on before it will begin to droop or drip or run? Same thing with coating. You know, like if you're painting elastomeric in the paint world, you might be able to apply it at 30 mils and it dries 15 mils dry. If you put it on at 35 mils, you might start getting some running. You want a sealant that has excellent hang time and workability because that it's a non-sagging product. You don't want to put something in that you have to worry about it's going to sag, droop, and maybe not be where it needs to be after application. And again, we talked about joint movement capability. In the real world, plus or minus 50% joint movement is absolutely outstanding. When you see products, I'm just going to throw it out there, not saying anything about anybody because, you know, that's not what we're doing. But when you see class 35, plus or minus 35, and saying joint movement of 70, you have to be in some extreme situation where that would make sense. And a lot of those products kind of scare us off because we think they're designed just to meet that number and they give up a lot of performance characteristics. Elongation is great. Most of the products we talked about today will give you between, say, 400 to 600 pretty regularly, and many will go up to, well, I won't say many, but a few will get up to 800% elongation. Recovery, though, is just as important. You need to get back to, if that joint moves back to where it was, you want to have a product that won't sag or droop there, that it can handle being stretched and then still work the way it needs to. I think a good example of that is, you know, if we've, those of us that still read books, you know, if you have a hardback book and you open it too far and you sort of break the spine of the book, that's sort of what can happen when certain sealants get maxed out. They get their spine broken and then they can't get back to where they started from. So, you know, look into that too when you're specifying things on that part of it. And then if you can get something that averages, say, 25 pounds of peel adhesion on common substrates, that's a pretty good product. To pass most of your ASTM pull tests for government projects, when we go out in the field and do tests, it only requires 5 pounds. To me, that's a pretty easy metric to meet. We look to try to find products and what we consider quality products, you know, with either within us or within our competitors, are those that can get up to that 20 to 25 pound peel adhesion after cure. And truthfully, if I were specifying buildings, I wouldn't put on anything less than that. You also want something that's going to be UV resistant, especially if it's not being painted. Very critical. Something that's good in all weather conditions. I think this actually might be almost a duplicate slide, so I'm going to move on. There's a durability test. I'll just go over this briefly. It's kind of a higher end test that you don't see advertised or talked about too much, but it's called a C1519 durability test. And what it does is it really is expedited conditions on how things perform over time. And I just thought it's kind of interesting to see how the polyurethanes do versus some of the others, you know, for instance, now this is what I was talking about. It also gives us some examples of things we're talking about. This is kind of a massive surface grazing over 4,000 hours of a xenon arc UV test, this is what can happen to some of their chemical technologies. The acrylics and all that, yeah, they take a little bit of beating. They don't look as bad, but same amount of time, they're still working. And a lot of these products will revert and go back and just lose their performance capabilities. Same thing here. We've got hybrids on glass and polyurethanes versus acrylics. So you get a little bit of that as well. Again, the aggressive testing, long-term performance can sometimes make a difference. And then just to show what we were talking about the grazing cracking, you know, I would say if you guys go by a strip center or a shopping mall or something and look for some tilt-up joints, you'll see this. This is where UV is beginning to break down some of the solvent-borne chemistries that are out there. So, you know, just something for you to keep an eye out and kind of better show you what I was referring to from our earlier part of our discussion. And basically, that's about it. So that's kind of a general overview. I'd be more than happy to take any questions or comments or anything else.
Hey, Kent?
Great job. Thank you very much. We do have some questions here. Go ahead.